Hello, everybody. Welcome to the second session of the string seminars this week. We're very happy to have Kajal speaking about joint statistics of the cosmological constant and supersymmetry breaking scales in Flux Vacua.
Thank you. Good evening, everyone. Thank you for the opportunity, for giving me this opportunity to present my work here. So I'll be talking about joint statistics of cosmological constant and SUSY breaking scale in Flux Vacua with Nilpotent Goldstino. This is basically mainly based on the first paper here, which I have done with Michele, Matteo, my guide Anshuman, and Kuvair. And the motivation for this work came from the last three work we did before this one. So those are also these papers. So this is a brief overview of what I will be talking about. So I'll give a little bit of motivation about string theory and compactification and the landscape, and why we are doing this statistics in the string landscape. And then I'll give the basic ingredients for the low energy physics in landscape, which will give us the exact formulae to compute distribution for this cosmological constant and the SUSY breaking scale. Then I'll go to statistics, and then I'll show my results, and then I'll conclude. Okay, so the main reason for doing string phenomenology is that this is only candidate available for us, which basically gives us a consistent treatment for quantum gravity. And the fact that it does that, it should be somehow able to reproduce what we see today in our universe. So it should be able to give a four-dimensional model, like standard model. And since right now we don't see supersymmetry, so supersymmetry should be broken. And also we should have some small cosmological constant explanation for that. And it should also come with extra ingredients like dark matter, inflation, dark energy, all those things. So a natural way to get to these kind of models from 10-dimensional string theory is to basically compactify the extra dimension. But when you compactify the extra dimension, you have this problem of having like large number of moduli fields. So to see that, you can take a simple example of a 5D pure gravity theory. And there you take this ansatz of this metric, where you basically take the metric to be this four-dimensional, and then decompose it into the other components. And once you substitute this metric back into this equation 1, you'll get something like this action 2. And there you can see you have this field phi, which is basically massless. And we don't want any extra massless field in 4D theory, because we already have almost all long-range forces. So we don't want any extra massless field. So what we need to do is basically stabilize this field phi, which is called the moduli field. And in generic string compactification, we compactify on Calabi-Yau manifold. And there, so you can see here that this field is basically, you can think of it as the G55 component, which is the compactified component of the metric. So for string theory, the Calabi-Yau is the compactified manifold. And there the metric can have like these two types of component. One is like either pure component, and the other one is like this M and N bar. And corresponding to these two components, you'll have different kind of moduli. So corresponding to these pure components, you'll have complex structure moduli, and they will be given, the number of these moduli will be given by the dimension of the 2,1 cohomology. And similarly for this scalar moduli, the total number of scalar moduli will be given by this H1,1 cohomology. Now, given these moduli fields, to stabilize them, we need to kind of like introduce fluxes in string compactification. And once you do that, you need to satisfy some conditions like this three. This is called tadpole cancellation condition, where this ND3 minus ND3 bar is the total D3 charge. And chi will be the Euler characteristics of the Calabi-Yau manifold. And if you think of this F3 and H3, which will take a form of like flux vector in this H3, which is the third cohomology of this manifold, then you can think of them as like a vector of this of dimension H3. And this condition will look like something of an equation of sphere, where the radius square is given by this chi over 24. Now for a generic compactification, this H3 will be of order 100, and chi will also be of order 100. And to get an idea of how many kind of vacua will be, which will be basically satisfying this condition, you need to just compute the volume of this sphere. And that will come out, if you take this example, it will come out around 10 to the power 500. So H3 is a kind of like dimension of the third cohomology group. So it's like F3 and H3 are belonging to.
That's like it's 1 + 1.
Yeah, something like that. Yeah. Yeah, it's exactly that actually. Okay. So given this large number of total vacua, we don't know why we live in this particular string vacuum. So, and we also don't have any tools to kind of like single out this vacuum out of these large number of vacua. So what one can try to do is try to see some low energy observables and try to get a statistical picture of those observables, so that at least if we'll not be able to pick out some set of vacua, we can at least eliminate some set of vacua who doesn't have like desirable property of this low energy observable. So that is the motivation of doing statistical analysis in the string landscape. Now I'll briefly describe the type 2B effective theory. So if you take type 2B on O3 or O7 or NT-fold, where this X is your Calabi manifold, then the 4-dimensional effective field theory can be described in terms of these two quantities. This is the superpotential, where F and H are your usual RR and NSNS field strength. And this omega is 3-form structure, holomorphic structure, and U will be your complex structure moduli. This T will be your scalar moduli, and this tau is axion dilaton. So all you need is these two quantities, which is the superpotential and the scalar potential. And once you have that, you can use this formula 6 to get 4D supergravity scalar potential for these moduli fields, which is basically given by sum of this F terms of these moduli and minus this M3 ½ which is the gravitino mass squared.
So this is n equals 1.
Yeah, n is equal to 1 after taking the orientifold. Yeah. Yeah. So if you remember, I said that to stabilize this moduli, we need to induce fluxes. But even after you induce fluxes, that is basically giving non-zero value to this W. And that is basically means you have some non-zero potential here. You can only stabilize this S and U. S is the axion dilaton and U is the complex structure, by which will in turn fix the web of this superpotential. But the scalar moduli, because of the fact that the volume takes a simple structure like this, where this is like scalar moduli to the power 3/2, what happens is this ft square basically cancels this minus 3m3 square, and at tree level you don't have a potential for the scalar moduli. So even after inducing fluxes, you need to go to next order in perturbation theory or in like any correction that so that you can stabilize the scalar moduli. So that is what I'll be describing next. Okay, and okay. Apart from that, so I was going to talk about nilpotent formalism for this. Okay, I should have included one more slide. So the thing is that even after stabilizing the scalar moduli, you're left with ADS vacuum, and in order to uplift that, you need to have some anti-D3 brane kind of sitting at either at the tip of the warp throat or some point in orientifold plane O3. So here I'll be talking about anti-D3 brane at the tip of warp throat. And so if you introduce the fluxes, then the metric of 10-dimensional manifold looks like something like this equation 8. And where if you go in highly warped region, that basically means that this V2/3 is much smaller compared to this exponential minus 4a. And in that region, basically this metric reduces to this equation 9. And we resolve the conifold singularity by introducing fluxes, and that will be kind of smoothened to this 3 sphere. And this factor sitting in front of this metric is basically takes a minimum value at that sphere, which is basically decided by the fluxes. So this K and M are kind of like flux vectors for F and H. Okay, and I'm defining it to Y because later we'll need this for simplicity. And this Y can be also think of in terms of this modulus of the shrinking conifold of on this throat. So that is basically what this Z is. So it's related to Z by power 4/3. Now, if we have this kind of setup, then you can compute the 4D contribution for this anti-D3 brane out of like 10D action. And that will look like something like equation 10, where this main point is that it's proportional to this quantity y, and you have this volume to the 4/3 sitting in the denominator. And this is for highly warped reason, because you don't want to go away from that. Otherwise, this will look like something volume square, and that is basically is kind of a decompactification limit even after introducing the fluxes. So yeah, so this is the setup for anti-D3 brane. Now, this anti-D3 brane, after taking orientifold, what happens is it kind of projects out all the bosons, and only we are only left with some fermionic fields. So that's how we say that it kind of breaks supersymmetry spontaneously. But in order to do some EFT, we need to, so, okay, just a second. Yeah. So in order to do explicit computation of this potential in 4D theory, we need some effective field theory to describe how this spontaneous supersymmetry breaking happens. And in this setup, we have a nice kind of like theory, which is basically given by this Nilpotent Goldstino. So this X is a chiral nilpotent superfield. And in terms of X, you can write, basically extend the Kähler potential and the superpotential. So this K0 is the K0 that I wrote earlier, which was basically the tree level Kähler potential. And then this W tilde, you can think of it as like either tree level, or if you're taking KKLT or LVS like construction, then it will come with a non-perturbative correction. And in addition to that, you'll have these terms, which will be basically given for this field chi. So there is no x square or mod x bar square sitting, because that is basically 0. That is what means this field to be nilpotent.
It's like matrix 7. X square equal to 0 means exactly what?
So if you just expand, write it in general superfield kind of expansion here, then it basically means there is only one degree of freedom left for this X. So this is auxiliary field, and this is kind of set to 0 because we want to preserve this Poincare like thing and set this side to 0. So we'll have, in general, the degree of freedom left of this X will be a fermionic degree of freedom, and that combined with the fermionic part of the Kähler moduli will give you the Goldstino of this.
So the point is this kind of thing can get faster.
Yeah, I think if you some non-linear supersymmetric, yeah, I think so you can get it, but right now I'm not able to. But let me think. Okay, you're saying like maybe not, like it's like kind of like matching these two. You have a.
Is it just a formalism, but it's an input Goldstino that any broken supersymmetric case can be regarded this way that?
I don't think so. I don't think so. It's only for the anti-D3 brane. That is also because we are kind of matching this contribution to the.
So the kind of supersymmetry breaking that takes place on anti-D3 brane, you are saying is gives rise to this input.
Yes. The leftover degree of freedom is basically this some nilpotent field, which we are identifying with this X. Yeah. So if you take these two equations, then you can compute the F term for this nilpotent field, which will look like this equation 13. And kappa here is basically the modular dimension of this field X under like modular transformation of the Kähler moduli, which are just generalized shift symmetries. So in order to identify this contribution with the anti-D3 brane contribution, you need to identify this parameter rho with the quantity y that we have written in previous slide, and you have to take kappa to 1. So once you do these true identification, then you can basically write the contribution coming from the anti-D3 brane in effective 4D theory using this nilpotent Goldstino. Okay. So now we'll do the Kähler moduli stabilization combined with this uplift coming from the nilpotent Goldstino. And I'll talk about two main models. One is KKLT and one is LVS. So in KKLT models, what we do in order to stabilize the Kähler moduli is that we add this non-perturbative correction to the superpotential. So this is a very simplistic toy model kind of thing I have written here. So once you do that, then the F term for the Keller moduli will not be exactly canceling the -3 m3 square sitting in the scalar potential. And you'll get something like equation 16. And minimizing this thing, you can basically find the expectation value of this field tau, which is here will be given by this 1/a log of W0. So this is kind of like gives you an idea that this W0 should be very small in order to the EFT of KKLT to be in like a working regime. So yeah, so this is the main equation to remember from here. And then, yeah, so in order for tau to be much, much larger, you need W0 to be exponentially small. And yeah, so, and in this case, the gravitino mass is basically, this is a general formula, which is the way we defined M3 in the first slide is basically this thing. And then once you substitute the wave of this volume in terms of the Keller moduli, then you'll get something like equation 17. And the fact that W0 has to be very small, that basically says that M3 in KKLT is basically controlled by this parameter W0, because there are other parameters sitting in GES and this N, calligraphic N, but the main quantity which is controlling EFT in KKLT would be the W0. And yeah, so that is kind of like what we did before adding the nilpotent field. Now, once you add the nilpotent field, this is field, some matter field phi, which lives on D3. We don't need to bother about that. So what we'll have is in addition to the KKLT potential we saw in last slide, second last slide, you'll have this uplift coming from the nilpotent field, which is basically given by this equation 20 here, where I have just replaced the volume in terms of the scalar moduli. And this will modify the total minimization condition, where you saw if you had just these two terms, then this will be basically tau is order log W0. But now you have this extra contribution coming because of the uplift. And yeah, that is kind of like giving, this is the contribution that is coming from the entity 3. Yeah, this rho square is basically what is the warping factor. Yeah. Yeah. So, oh, little a was the sitting in the exponential, so it's this thing, which will be 2 pi by n, depending on what kind of like gauge group you are taking on the. So it's okay. So now, since you have so without this uplift, this cosmological constant lambda would have been just this first term, which is nothing but -3 m3 square. But now you have this uplift, which gives you a freedom to kind of like tune this lambda to any desirable value, as long as you are not kind of like going out of this EFT regime. So yeah, so this is lambda, where this quantity you can think of it as -3 m3 square, and this is the y parameter which I talked about earlier. And all these taus will be replaced by their vacuum expectation values. Yeah, so just a second. This is basically rho square is y, and this is basically flux given in terms of the flux vectors. Okay, right. So the main thing to take away from here is that after basically substituting the wave of this tau here, you will be left with only 3 parameters, which will be the string coupling, because if I go back, so it was given in terms of W0, and there was some, if you write it, yeah, because M3 is sitting there, there will be string coupling also, and W0, and in this extra parameter y. So you'll have lambda written in terms of these 3 parameters out of this EFT. Now, if we go to LVS, then the main difference between LVS and KKLT is that in addition to this non-perturbative correction to superpotential, we also have this kind of like leading order alpha prime cube correction to the Keller potential. And I have taken a little bit not very simple, but it's required form for LVS kind of. So the volume of the Calabi-Yau is given by two Kähler moduli. This is tau b means big, which is basically controls the volume, and tau is just there to give this non-perturbative correction. And once you use that these two quantities, you can again use the formula for the scalar potential and arrive to this equation 25, where you can stabilize for these three moduli fields and their axionic counterparts. And in this case, because of this extra additional correction, what happens is that this volume is stabilized exponentially in this moduli fields, which is this tau s is again stabilized in this 1/gs. So since gs is less than 1, that basically tells that this volume will be very large. So that is how its name comes, which is large volume scenarios. And again, you can see that all these stabilized quantity are given in terms of this W0 and GS. And AS and capital AS, you can think of it like some constant order 1 parameters, will not be bothered about that. And in case of LVS also, we are initially we will have this ADS non-supersymmetric vacuum. And here the main quantity controlling everything will be the string coupling. Because everything is given in terms of this exponential 1/gs. So the main parameter controlling LVS will be the string coupling. In KKLT, it was W0, which was the web of the superpotential. Now, if you do the similar analysis for LVS here, then what will happen is you'll get a cosmological constant, which again will depend on the three parameters, which is W0, and then volume you'll write in terms of G string and this Y. So yeah, and in both cases, the gravitino mass basically remains same at leading order. Only thing changes is this lambda. Okay. So now I'll talk about statistics. So previously, which was initially done by Denef and Douglas, the way they defined this number density was they initially, they assume that near lambda equal to 0, you can kind of decouple the distribution of everything else from the cosmological constant. So this is basically delta function. This is kind of like setting the cosmological constant to 0. And here they missed one thing, which was the Kähler moduli F term, because I think at tree level, it was kind of flat. So maybe that was the reason. So it's this equation 31 is kind of wrong right now. So what we are trying to do is incorporate the Kähler moduli F terms as well in this distribution. And for this talk, the main thing is that we are also not assuming that this distribution of cosmological constant decouples from the rest of the distribution near lambda equal to 0. So the motivation is that first you do the joint distribution, then go to lambda equal to 0 and see if there is a decoupling happening there or not.
So, Denef and Douglas, what term they did account for?
So this d square fs, which is the axion dilaton f term, and then fu is the complex structure, but they didn't take the Kähler f term, Kähler moduli f term. But that basically governs how the final distributions will look like. We'll see for both KKLT and LVS. So if you assume that this is true, then you can basically reduce the distribution in terms of, let's say you are looking at the SUSY breaking scale. So it will be given in terms of just M3/2. And without Kähler moduli stabilization, this density was kind of linear in it was constant. So the overall distribution we'll have for all set of models will be this power law distribution for SUSY breaking scale. But, okay. But we'll see that it's not true. And before seeing that, we need to kind of understand the statistics of all different parameters that we are using. So the main parameters we are interested in is string coupling and the wave of the superpotential and this hierarchy Y, which is basically the constant sitting in the numerator of the uplift, which is set by the fluxes. Now for G string, we checked for a simple example where you can take a rigid Calabi-Yau and there this tadpole cancellation condition, which I showed in maybe second or third slide, will look something like this, where L is some bound you set because of this QD3 charge. And then this A is basically A1 plus IA1, and B is basically B1 plus IB2. And then what happens is this condition here, you only have to solve for all the A1, B1s which satisfy this condition. And this condition here has this SL2, Z symmetry. So you can basically exploit that and try to find all values of tau and map that to the fundamental domain of this tau. So it will look something like this. And now the string coupling is given by like imaginary part of 1 over string coupling is given by the imaginary part of tau. So from there, you can basically derive a distribution for the string coupling. So, and the fact that you can see the density is much higher near the lower part of this fundamental domain, because as you go high, it gets harder to satisfy this tadpole cancellation condition. So that is the reason why we see this uniform distribution for GS, because it's like 1 over GS and you get something like this for tau. So that we checked for this simple case, and many other people checked it for much general case, and they arrived at the same conclusion. And not only at orders like 0.1 or something, it's uniform, but even at much smaller values of string coupling, it's kind of uniform. And apart from that, we have this tree level wave of superpotential W0. And that basically the distribution of this tree level superpotential is like a uniform distribution for a complex variable, because you take a continuum limit and compute this delta dW, which was kind of like F0 F term condition for supersymmetric cases in KKLT. And you see that you will find simple analysis you can do similar to the G string we did, and you'll see that it kind of like distribution of this W0 looks like something, question 34. And apart from that, we have this parameter hierarchy, which is determined by the vacuum expectation value of this shrinking conifold modulus. So if you remember, y was something mod z to the power 4 by 3. And this distribution for this mod z is given by the pre-potential square of this z. And in this term, the main feature for this distribution basically comes because of the metric sitting here. So the metric will give you something like a log. And because of that, we get something like equation 5, where I have made the change of variable from z to y. So in y, you'll get some constant sitting, and then you'll have this 1 over y log y square. So these are basically the distribution for all the parameters that we are going to use to derive the distribution for supersymmetry breaking scale and the cosmological constant. Okay. Yes. So that is what we are, the main assumption that we are making. If you have like enough number of fluxes and these three are not related to each other in like any kind of like equation, then we assume that these are like uncorrelated quantities if you take the distribution.
Let's say like this GS.
Yes. Sorry, why
Why is GS not why?
Why? Right. I think the main motivation is that all these three quantities are given in terms of fluxes, which we assume that they are kind of like all random integer value. So they, and you don't have in these kind of vacua, you don't have a direct relation between these three quantities. So because of that, we assume that these three quantities are kind of like independently distributed. And then you use that assumption to use this equation for lambda and M3 and kind of like scan over the vacuas for KKLT and LVS and find the distribution for.
Let's say like I take that.
Yeah.
Compute these three numbers.
Right. Right. Whether they are, yeah.
So if they're really uncorrelated,
To be 0. Oh, yeah, diagonal, yeah.
So is that what happens? You just take some set of flux back from there.
So I don't know like how to kind of like do that to take like, because for W0 you basically assume, for the distribution of W0 you assume that the complex structure moduli, the F terms are kind of like uniformly distributed, but I don't know if anyone has like verified that. So we are using kind of like assumption of Deneb and Douglas here. But yeah, but other than the fact that if you have enough number of fluxes, then you can assume that these three quantities are kind of like uncorrelated. I don't think I have an answer. So
Since you have already expressions for these terms of the fluxes,
yeah,
you have directly what kind of fluxes that you that they are discretely distributed, say below a certain value.
I mean the distributions are derived like that only for W0 rho and GS, but how will you check that they are kind of uncorrelated to each other?
You can also derive the joint distribution. Generally, if I derive covariance factors. So we have some expressions for these three quantities in terms of a lot of numbers.
In terms of, yeah, fluxes, we have, yeah.
Then you could just put random numbers in fluxes and then ask for you get filters for every set of fluxes, for example, three values.
Right.
So you can just put that, and for the data you can calculate the 3%.
Right.
I mean, that tell you whether the diagonal, and you can even ask, what you can do some principal component analysis, say like what really are
Right.
correlated directions
Right.
by diagonalizing the covariance.
Right. Okay. Yeah, I think, yeah, it is doable, but for this work, we kind of like assume that they are uncorrelated.
In fact, I mean, if you are ultimately interested in distribution of the supersymmetric breaking scale and the cosmological constant,
Yeah.
you can just forget about these variables and express those in terms of fluxes, and just do the distribution as a fluxes.
So
probably is more.
actually, that is what we are trying to do right now. So yeah. So but because initially we thought that if we do this kind of like analysis, then we'll get back the usual distribution for KKLT and LVS, which I'll show right now. But the results were drastic when you do the joint distribution and the kind of decoupled distribution. So then we started doing similar things for other kind of models, and there we are using, here I'm using the Nilpotent Goldstino to uplift the ADS to DS. But in right now what we are working on is that we are kind of like taking a non-zero value for F term for the complex structure, and then from there we are getting this extra parameter and try to kind of like see if we get similar kind of results there. But the fact that this F term for a complex structure is not, so there will be three quantities mainly, if I say, so it will be like Fu will be some epsilon times W, maybe mod square will be there. So something like this. And the fact that this F, epsilon and W, out of these three, only one quantity is independent. So there we are trying to kind of write everything in terms of just the flux vectors and the flux quanta and see if we'll get some distributions. So that is what we're trying to do. Okay. So if you assume that these are basically the distribution for these quantities, then we can derive some distributions. So let's say first we look at the distribution assuming the decoupling of cosmological constant out of like total distribution. Then for LVS, if you remember, the gravitino mass was given like exponential 1 over GS. And you can simply calculate that this distribution for gravitino mass for LVS is this logarithmic distribution. And similarly, you can do that for KKLT as well. But in KKLT, the main parameter driving everything was this W0, and W0 was distributed as a like uniform complex number. So there the distribution for this M3 up is this power law distribution. But the generic feature of these two distributions that they kind of favor the higher SUSY breaking scale here. But if you try to take the joint distribution, so yeah, so the main assumption that we are taking is what Loga was saying, that we are kind of taking this all three quantities to be uncorrelated. And based on that, we use the structure of the vacuum for LVS and KKLT and kind of like do this change of variable going from these three parameters to whatever quantity we want to find like distribution of. So that is the main theme of this joint distribution. So if you go for KKLT, then the change of variable you'll have to do would be W0 and Y going to lambda M3 half for some string coupling, because the main, so because string coupling was not doing anything in case of KKLT. So mainly you will be focused on these two parameters. And then what we saw is that once you do that and take, because the expression was very lengthy, so I'm just showing this result. So once you do this change of variable and take lambda equal to 0, what you get is something like equation 43, which is drastically different from the result we got for like assuming that the distribution decouples. So it's like this favors some lower scale of SUSY breaking. And the main reason why it is happening is because of this 1/y factor setting in this distribution of the hierarchy. So that basically tells that it's highly model dependent, like what kind of uplift you are taking. And so you can see here I have plotted for fixed value of lambda. One is like lambda equal to 0 and then ds and ads. And these, if you take like a very high value of M3 up, then basically they will kind of like merge together at some point. But they have like distinct feature where M3 up is less, but those are not the values that we need to concern ourselves with, because the depth of the ADS is kind of set by M3 up, so you can't take M3 up to be much smaller than lambda. So and this is a plot for like total this row where we kind of like took both lambda and M3 up, and the cutoff value you're seeing here is decided by like not going to the decompactification limit, and this is basically the cutoff value for not taking M3 half to be much smaller than lambda. So this is the distribution for KKLT.
You see that if supersymmetry scale is smaller, the cosmological constant is
likely to be
bigger.
It's the other way, right? If the cosmological constant is small, then the supersymmetry scale, breaking scale is likely to be small, right?
Lambda is small.
Then
the gravitino is
it's favoring small value
Because of small y.
because of this 1/M3 up.
So you say smaller cosmological constant favors like that.
I think I don't know if I can trust these three like distinct feature of these lines, because for at least for ADS you can't go beyond lambda equal to -3 M3 up square for any of these vectors. So in a sense that what we're saying is that for small cosmological constant value, if you're taking this model, then you will have a small value of SUSY breaking.
But small value is
so okay.
Because let's say the cosmological constant is like
I mean, it's not that I don't know if I'll say it like that, but it's like you're getting less and less of this vacua if you go higher to the higher value of the M3. So it's like highly probable that you are in lower. Okay. But I don't have a number really, so we didn't we basically check.
Just multiply this by M3 half and integrate from.
No, the thing is that you have to also integrate over the fundamental domain of this axion dilaton, and Yeah.
So those will be order one.
Yeah, those will be order one effect, but yeah, I think the point of this work was that we were not getting this decoupled kind of distributions near lambda equal to 0. So we kind of stopped there because we were kind of making a point. But yeah, we're trying to do a more general thing right now. So maybe next time I'll give some numbers.
Say, why do we expect that the gravitino mass?
It was the assumption that was taken before. So
obviously gravitino mass is very
no, the thing is that for Denef and Douglas, they didn't focus on the scalar moduli F terms, and scalar moduli are basically what setting the scale of M3 up, right? But they focused only on the complex structure and the accidental electron. So for them, it makes sense to kind of assume that it will decouple from the.
So if we ignore the log in that numerator, then
Yes.
it's basically logarithmic distribution, right? The Tm over n. Right?
Yeah. Yeah.
So log m is uniform distribution.
Yeah. I mean, you can. Yeah, you can say that. Yeah.
And earlier in KKL.
If you take lambda equal to 0, then only, right?
Yeah.
Yeah. Yeah.
So earlier what was the result?
It was M3 square. After integration, the number density was going like M3 square. So let me just
The distribution was m.
this was the.
I see. So they are the low value of gravitino mass are ruled out.
Yeah.
Very small.
Yeah. Yeah. Yeah, I mean, there will be a constant sitting here, but yeah, you can say that it will be less and less probable as you.
You see m square versus that's the announcement.
Yes. And for LVS, we were finding this logarithmic distribution to begin with. But when you do the joint distribution, you'll get like highly suppressed density here. So it's like 1 over M3 up to the power 4. And
then it's a lot. That means that low masses are more likely.
yeah, in this setup, yeah, that is what it says basically. I don't know if you can like say it in general because we are kind of restricting to a very specific uplift model. So initially we were thinking that maybe it's like we are looking at a very small subset of total landscape. And then if you sum over all those subsets, then you'll somehow get back the result that we are getting. But we don't have like enough data to do that actually. But yeah, that could be like one explanation, but the thing is, it's like completely different thing that we are doing compared to what we did earlier. So,
but if this is the case, then this means that the LVS problem is ruled out already. Like you haven't found those customers.
yeah, I mean LVS or maybe Nilpotent Goldstino formalism is kind of like not good to look at.
But that you said that once you like this uplifting, it's just a consequence of that.
No, the thing is that here the main parameter which kind of gives you distribution is this y, and that y is specific for what kind of uplift you are taking. So the distribution of y is kind of important. So yeah, so the main thing, because right now what we're trying to do here, it's like this epsilon will be the parameter instead of y. So what kind of distribution we'll have for epsilon will decide what kind of distribution we'll get here.
To rule out LVS, you also need to know how low is low for
Because if you have one over n, distribution is high, big, they are small n. Okay. You do the other tracks, I mean, breaking scale cannot become smaller than standard model scale. Okay. But then, if you don't have any other constant, then it will be highly big just beyond the standard. Right?
Yeah.
The probability that it's far out is very small. Right, from this.
Right. Yeah, I mean, it took a really long time for us to like make sense of these results because we were expecting to get something else. And still we don't know actually, like, unless you have like large set of uplift different uplift, you don't know what will the total landscape picture will look like.
The upper part of landscape are not accessible.
Yeah.
You get stuck in this part.
Right.
It does happen. Let's also assume that the way you uplifted and stabilized.
Yeah.
Actually stabilize the model.
Yeah.
So if you find yourself in this part of the model space, this one is.
Yes. Yes.
So at least, I mean, you can say that this is not.
This is not, yeah, good enough. Or
So you can rule out this part of the space.
right. I mean, yeah, in some sense you can say that. Yeah.
But yeah, the worrying thing is that like this assumption of uncorrelated.
Yeah.
But that I think can be repaired by what? Yeah. Looks like more a technical problem than.
Yeah. So the thing is that, and also you can estimate of left rule out. You can just calculate some average or something, and then just see that these scenarios, at least with this kind of assumptions, is not possible.
You are saying like compute some expectation value for this sum.
So put a prior on lambda. Be that it would be, let's say, maximum
Less than.
the observed lambda.
Right. Right.
Then you can say, like what is the expected value of M3?
Right.
The expected value of the gravitino is much better than what the bounds are.
I mean, if you're taking, okay. Right. Okay.
You can say that, like, I mean, this is what, I mean, this is not the place where it will be for.
Yeah, in some sense, you can say that, yeah, here also that nilpotent, this, at least LVS for this formalism is a not good thing to be focused on. So maybe if we are able to do that, then we'll see if it's like in general true or not. Okay. So yeah, these are like kind of the main results that I had to show. So I'll conclude now that we studied the joint distribution of gravitino mass and cosmological constant for both KKLT and LVS models, where we took the uplift coming from this NTD3 brane. And if you assume that if you assume that there was a decoupling of this cosmological constant and supersymmetry breaking, then you are getting higher scale of supersymmetry breaking near lambda equal to 0. But if you don't assume that, then the distributions are highly suppressed towards the lower values of M3 And there was this suggestion by Susskind that if you add like more sectors for the uplift, then somehow you can kind of like play with these parameters and get back this uncorrelated distribution for lambda and M3 But what we saw that if you take the similar kind of uplift, then you can basically take the sum of these parameters to be a new parameter. Then apart from a kind of theta dependent term sitting in the distribution, you will get the similar result. So there also it's highly suppressed near lambda equal to 0. Yeah. So, and the main thing which was leading to this result was the distribution of this throat hierarchies. That was kind of like a main thing which was giving this 1 over M3 up to the power 4 kind of thing for LVS and 1 over M3 up for the KKLT case. Now, before ending, I'll just say some remarks. So for KKLT, we require this very small value of W0, but we don't really know. I don't know if anyone have like checked whether this W0, the uniform distribution of W0 is still valid at exponentially small values. And there was this construction by McAllister et al., where they constructed this perturbatively flat vacua, where W0 was kind of given by this exponential minus 1 over GS. Then if you take only those set of vacua, then the results will be similar to LVS, because in LVS we were getting this kind of thing. But we in our like one of our paper, we have shown that these kind of vacua are very sparse if you look at it in a statistical way. So we really don't know what will happen if you go to really small values. Even you take some asymptotically or approximately flat, perturbatively flat vacua, then also there is no kind of like statistical picture to look at, because you get very less points to really analyze. Yeah. And and we also have seen that this joint distribution was kind of like heavily dependent on what kind of uplift mechanism we are taking and the parameters coming in the uplift mechanism and their distribution. So this basically gives us motivation to do similar analysis for all available uplift mechanisms and see if we can get a kind of like general picture out of these kind of analysis. So, okay, thank you. I think I finished quite early.
That leaves us with more time for questions if there are any.
Making sure that yes. So let's say I have a fixed value of lambda.
Yes.
And let's say I got some random flux.
Okay.
And I calculate using these two components. And let's say I look at the case that I get the same lambda input.
Right.
Are you saying that the LVS usually is lighter? Than
Yes.
that's
Yes. Yes. Let me just think. Let me think a little bit because in this regime we are taking lambda to be much smaller than M3. So that is kind of like a thing with this has been derived. That we expect, yeah. So as long as you are in that regime, you'll get this answer. Yeah, you'll get.
So I just pick some fluxes that lambda is much less than M3 half. And but I want to get this lambda from KK.
Yes.
Without this,
yes. So you'll have like, yeah.
The formula that we had and the LVS cycle. They say the M3 half associated with a particular lambda is smaller for the LVS.
Yes.
The distribution has 1 over M.
4, yeah.
And there it was Dm over M.
Yeah. Yes, LVS is highly suppressed in this case. Yeah, very highly suppressed in the sense like in terms of like values of M3 up. So if we,
very light.
Yeah, very light. Yeah. Yeah.
Any more questions? If not, let's thank Kajal again.
Thank you.